Hello everyone, in today's video we're going to talk about the Hille equation, more precisely the existence, uniqueness and regularity of the solution. Let's begin with some notations. Let omega be included in Rn, an open set, and gamma its boundary. We denote Q equals to omega times 0 plus infinity and sigma equals to gamma times 0 plus infinity. Sigma is the lateral boundary of the cylinder Q, as shown on the figure below. We consider the following problem: finding a solution uxt in omega bar times 0 plus infinity going in R such that we verify the three following equations, where delta is the sum of the second partial derivatives, stands for the Laplacian with respect to space variables, and t is the time variable u0x, a given function. The first equation 1 is called the Hille equation because it modelizes the distribution of the temperature U in the domain omega at time t. The Hille equation and its variations occur in a lot of diffusion phenomena. The Hille equation is the simplest example of a parabolic equation. The equation 2 is the Dirichlet limit condition. It can be replaced by the in-domain condition 2' with n the outward unit normal vector to gamma. 2 can also be replaced by other conditions. Condition 2 is expressing that the boundary gamma of omega has temperature equal to 0. 2' expresses that the flux of heat across sigma is 0, because if we look at the little illustration over here, the gradient of U, so the variation of temperature, is perpendicular to the vector n, and it means the variation of temperature across the boundary is equal to 0. The third equation is the initial condition of the Cauchy data. We're going to solve the problem 1, 2, 3. We're considering uxt as a function defined on 0 plus infinity with values in space h, where h is a function space which depends only on x. For instance, h equals to L2 of omega, or h equals to h1 0 of omega, and so on. Consequently, the notation ut will assign an element of h, that is to say, the function that gives uxt for x at a given t. So ut of x is equal to uxt with t fixed. This method allows to obtain easily a solution for the problem 1, 2, 3, gathering Hille-Yosida type results and other results from chapter 7, 9, and 13 of the Hille-Yosida book, Functional Analysis and Partial Differential Equation. I'm gonna show you these results later. Let's say that omega is infinity with gamma bounding. The theorem 10.1 says that if we suppose u0 is in L2 of omega, then it exists a unique function uxt that verifies our three equations and condition 4 and 5, and also u will be in C infinity of omega times epsilon infinity. So we need to be a little more exhaustive with the notation in 5. What does it mean? It means that u is in C1 with respect to the time variable t when x is fixed. On the contrary, u is in L2 of omega when the time variable is fixed, when we're looking at the x variables only. Finally, u will be also in L2 of 0 infinity and h1 0 of omega, and we have the sixth condition too. The proof: we apply the theory of Hille-Yosida in the space h equal to L2 of omega. In order to do this, we introduce the non-bounded operator A that goes from dA included in H towards H defined by d of A equal to H2 of omega intersected with H1 0 of omega including L2 of omega. The operator A is simply minus Laplacian of U. We observe that the condition 2 is incorporated in d of A. Now we are going to verify that A is maximal monotone and self-adjoint. We will apply the following theorem 7.7. This theorem says that if A is maximal monotone and self-adjoint, then for all U0 in H, there exists a unique function verifying the following conditions. The proof will be shown in another series of videos coming soon because it is quite long. So the goal is to show that A is maximal monotone and self-adjoint in order to apply the theorem above to get the existence and uniqueness of 1, 2, 3, verifying 4, 5, and the rest. A is monotone. Indeed, if U is in D of A, we have the scalar product, the L2 scalar product of AU and U will be equal to the integral of minus Laplacian U times U, which is equal to the integral of the absolute value of the gradient of U squared, which is positive, because U is equal to 0 on gamma. U is indeed in H1 0 omega, and according to the proposition 9.18, if omega is C1, U in L2 of omega, then U in H1 0 omega is equivalent to U equals to 0 on the boundary. We need then to show that A is maximal monotone. It suffices to show that the images of the identity plus our operator is equal to H equals to L2 of omega. But we know that for all F in L2 of omega, there exists U in H2 until H1 0, a unique solution of U minus Laplacian U equals to F. This results from the theorem 9.25, regularity of the Dirichlet problem, shown later too. Here we saw that L2 is included in R E plus A, but we also know that if U is in the intersection and verify U minus Laplacian U is equal to F, so F is in the image, and then U minus Laplacian U will be in L2 because U is in L2 and Laplacian of U is in L2. To examine the integrability, we then need to finally show that A is autoadjoint due to the proposition 7.6, which states that if A is maximal monotone, is a maximal monotone operator and symmetric, then we know that A is self-adjoint, proved later too. So let U V be in D of A, we have scalar product of A, U, and V in L2 is equal to the scalar product of U and AV, and then A is symmetric, so is self-adjoint. On the other hand, the theorem 9.25 says that if omega is Cm plus 2, and if, so in our case it's okay because we are seeing infinity by hypothesis, and if F is in Hm of omega, then U will be in Hm plus 2 with the continuous embedding More precisely, we have d of a l is equal to the u in h2l of omega, such that u equal Laplacian of u equals to Laplacian l minus 1 of u equals to 0 on the boundary, because a of u is minus Laplacian of u. So we apply a another time, we got Laplacian squared of u. And a of u, by definition, will be in h2 of omega intersected with h1 0 of omega. So minus Laplacian of u is in L2 of omega, and Laplacian of u is equal to 0 on gamma. It goes to the following equality, and so Laplacian of L minus 1 of u is in h2 of omega intersected with h1 0 of omega. So Laplacian L minus 1 of u is equal to 0 on gamma. Following this, we know from the theorem 7.7 that the solution u of 1, 2, 3 belongs to ck 0 plus infinity d a l for all k all l. And thus u is in ck 0 plus infinity h to l omega for all k for all l, with corollary 9.15, which says that WMP of omega is included in ck omega bar if m minus n over p strictly positive is not an integer with k equals to the integral part of m minus n over p. We take m equals to 2l and p equals to 2, so h2l is in ck of omega bar. It results from this that u is in ck 0 plus infinity ck omega bar for all k, which can be written as u is in c infinity omega bar times epsilon plus infinity. And that's one of our conditions we just obtained. We can get 4 and 5 by applying the theorem 7.7, which says that there exists u in the following intersection, and replace with h equals to L2 of omega and dA equals to our intersection. Thus we have the condition 4 and 5. Finally, we only have to show 6. Now first we need to prove that the function giving uxt for t is in L2 0 infinity. We look at the function giving uxt for t with x fixed. To determine if the following integral converges, we have to consider the behavior of the absolute value of uxt squared when t goes to infinity. The solution of the heat equation is given by uxt equals to the integral of omega of j of x minus y t u0 y dy, with g the heat kernel. To examine the integrability of the absolute value of the temperature squared on 0 plus infinity, we got to evaluate the following integral. So we replaced with the expression of u we just saw, and we use the Cauchy-Schwarz inequality to upbound our absolute value squared of the main term of our integral. As the initial term u0y is L2 of omega by hypothesis, the integral is bounded, and gx minus y t is also bounded. We need to study the asymptomatic behavior of gx minus yt when t goes to infinity. The sheet kernel is given by the following function. When t goes to infinity, 1 over 4 times p times t is the square root of 4 times p times t goes to 0, meaning our function g goes to 0. So for a given x, our function g is rapidly decreasing to 0 when t goes to infinity. It means that our integral is bounded, so t giving uxt is in L2 0 infinity because of uniform convergence. Now we can prove 6. Multiply 1 by u and we integrate on omega times 0t. We consider the following function phi. Phi is c1 on 0 plus infinity according to 5, and the derivative of phi is given as follows. So if epsilon is set between 0 and plus infinity, and t is also strictly set between 0 and infinity, we have our last result, and we just have to make epsilon goes to 0 to obtain that phi t minus phi 0 is equal to minus the integral of from 0 to t of the absolute, the normal 2 of the gradient of u t squared. So that is the end of our video. If you have any question, don't hesitate to ask them, and to be kind to leave a like and to subscribe so the channel grows a bit. Thanks for watching. Goodbye.